Alright, so we're going to have a look at another ordinary differential equation. Ordinary differential equation. This time we will be having a look at an integrating factor differential equation, but this integrating factor differential equation is going to be a little bit messier than the last one, and it's going to have an initial condition. So we're going to need to find a general solution and a specific solution. So the question is dy dx plus e to the xy over e to the x plus 1 is equal to x over e to the x plus 1 such that y of 0 is equal to 1. So this is a more messy first order differential equation. It's not separable, so we can't use the separable method, unfortunately. So this is exactly of the form we need to do integrating factors. So our integrating factors work for a first order DE of the form dy dx plus p of x times y is equal to q of x. We know the integrating factor is some constant a times e, where e has the power, the integral of p of x dx. So this is an integrating factor, and if we have this integrating factor, this implies that the solution, y, is equal to 1 on the integrating factor, I of x, times the integral of the integrating factor, I of x, times q of x dx, plus c over I of x. Now this just comes from the integral. This is just a constant that we would get when we did the integral. But this is the format that we're going to be using here. So first we need to find the integrating factor. So integrating factor is our first step. So I is going to be a times e, where e's power is p of x, the integral of p of x dx. Now over here we can see p of x is going to be equal to everything that gets multiplied by y. This will be e to the x over e to the x plus 1. And q of x will be everything on the right hand side of the equation. So q of x will in fact be x on e to the x plus 1. So I is equal to a times e to the power of the integral of e to the x over e to the x plus 1 dx. Now this looks a little bit complicated, but this is just a natural logarithm because the numerator is the derivative of the denominator. If the numerator is the derivative of the denominator, it's just the logarithm, natural logarithm of the denominator. So this means integrating factor is a times e to the nat log e to the x plus 1, and that is plus some constant, which we might call, maybe we'll call it alpha. Now this constant really we're just going to make equal to 0, because if we expanded this we would have a times e to the alpha times e to the natural log ... This is all just a constant. So a, e and alpha are all just constants anyway. So we're just going to let the alpha be 0 and we're going to leave the a out the front. So this just goes away. So this means I is equal to a times e to the natural log. Well, e and e to the natural log, they cancel out. So this is just a times the absolute value of e to the x plus 1. Absolute value of anything takes that thing and makes it positive. So if the thing in the absolutes could be negative, you can't just turn it into brackets. If the thing in the absolutes can't be negative, you can just turn it into brackets. E to the x plus 1 is always positive anyway. So this is just going to become a times e to the x plus 1. So this is pretty nice. We now have our integrating factor, I of x, is equal to a times e to the x plus 1. So this is the first thing we need. Now we're going to use this in order to find the solution. So first we're going to find the general solution. So y of x is equal to 1 over the integrating factor, a times e to the x plus 1, times the integral of the integrating factor, a times e to the x plus 1, times q of x. Now q of x, we said on the other side, was x over e to the x plus 1. So times x over e to the x plus 1. This is very convenient. These e to the x plus 1s will cancel out. Dx plus a constant over the integrating factor, which is a e to the x plus 1. Forgive my slightly squishy writing here, but we can clearly see this still. So this is going to be the solution. We just need to neaten this up a little bit. So y of x is equal to 1 over a times e to the x plus 1 times the integral of ax dx. Well, the integral of ax will just be ax squared on 2. So that is a times x squared over 2. And then at the end we have plus a constant over a times e to the x plus 1. So now we can try and condense this a little bit. We can try and get it into a single term. This will become, we can put a 2 down here, a 2 up here, and we can say a x squared plus 2c all over 2a times e to the x plus 1. Now we have some a's and a c. These are all just unknown constants. So if we cancel the a's, if we divide everything by a, so divide this term by a, divide this term by a, divide this term by a, these a's will cancel. And the c divided by a, that's still just some constant. So actually the general solution will be x squared plus 2c. We can just actually call it c because it's just some constant that we don't know yet, divided by 2 times e to the x plus 1. Now if you wanted to be really careful, you would not call this c. We might call this d, because d hasn't been used yet as a constant. So this is our general solution. Now that we've got the general solution, we need to find a specific solution using our initial condition y of 0 is equal to 1. So now we're just going to plug this in. So y of 0 equals 1 means that y is equal to 1 when x is equal to 0. So we get 1 is equal to 0 squared plus d over 2 times e to the 0 plus 1. Now e to the 0 is just 1. 2 times 1 plus 1 is 4. 0 squared is just 0, so we get 1 is equal to d on 4. Therefore d is equal to 4. And this means our specific solution, the solution once we take the initial initial condition into consideration, is in fact y of x is equal to x squared plus 4 over 2 times e to the x plus 1. So this is our specific solution. And that's, in a sense, the end of the question. That's what we've been asked to find, but we're not actually finished, as is usually the case with these higher order questions. You really want to check this, right? You can confirm that this is actually the case by differentiating this, plugging it back into the original function, and proving that the left-hand side is equal to the right-hand side. So that's what we're going to do. We're going to check, and we'll do our check over here. So first we need to find the derivative. So if y is equal to x squared plus 4 over 2e to the x plus 2, this is a quotient rule, so u and v. U is equal to x squared plus 4. This means u prime is equal to 2x. V is equal to 2e to the x plus 2. This means v prime is equal to 2e to the x. Now this implies that dy dx is equal to u prime times v minus u times v prime. U prime times v, that is 2x times 2e to the x plus 2 minus u times v prime, that is 2e to the x times x squared plus 4. It's in the other order, but it's more convenient to write it this way. All over v squared, which is 2e to the x plus 2 squared. Now, this question, I'm actually going to expand that numerator while I'm here. I'm going to expand all these brackets. So I'll get 4, we'll get 4 x e to the x plus 4x minus 2e to the x times x squared is minus 2x squared e to the x. 4 times 2e to the x is minus 8e to the x. This is all over 2 e to the x plus 2 all squared. Well, we can factor 2 out of both of those, and this will give us 4 times e to the x plus 1 squared. The reason we're doing that is we know the right-hand side of this equation up here is over an e to the x plus 1, and so I'm making that denominator an e to the x plus 1 straight away. You don't have to do this. I'm just doing this because I know this is what I'm after. So now that we have the derivative in this form, we now need to plug the derivative and the function into the left-hand side of this equation. So this is the left-hand side. We're going to plug the derivative and the function in here and then try and show that this is equal to this right-hand side. It's just easiest to do it this way as opposed to rearranging the whole equation to get something that's true. We just work on one side, and these ones actually work in quite a nice fashion. So we have the derivative, which is 4x e to the x plus 4x minus 2x squared e to the x minus 8 e to the x all over 4 times e to the x plus 1 all squared. And then we need to add e to the x over e to the x plus 1 times y. So this will be plus e to the x over e to the x plus 1 times by y. That's the thing we have over here. That's our specific solution. X squared plus 4 over 2 times e to the x plus 1. So if we expand this second term, we could also cancel everything in the first term by 2, divide everything by 2. This becomes 2, this becomes 2, this becomes 1, this becomes 4, this becomes 2. We're doing that because we're going to get to 2 down here. So this whole thing becomes... these will now have a common denominator, by the way, because e to the x plus 1 times 2 times e to the x plus 1 will be 2 times e to the x plus 1 squared. So we can put everything over the common denominator. We'll get 2x e to the x plus 2x minus x squared e to the x minus 4x, and then we have plus e to the x times x squared, so it'll be plus x squared e to the x, and then e to the x times 4 will be plus 4e to the x. This will all be over 2 times e to the x plus 1 all squared. So we have a few terms that we should be able to cancel or simplify here. We just have to do it in a way that's very careful. So this is not a 4x, sorry, this is a 4e to the x. This is this term from up here, 4e to the x. So now we have minus 4e to the x plus 4e to the x, they're gone. Minus x squared e to the x plus x squared e to the x, they're gone. And so now we can factorize 2 from the numerator. We get 2 times x e to the x plus 2x over 2 times e to the x plus 1 squared. 2's cancel. Now we can factor x out of the numerator. We get x times e to the x plus 1. This 2 got factored out. So x times e to the x plus 1 over e to the x plus 1 squared. Well, the squared and the e to the x plus 1 will cancel. This is x over e to the x plus 1, and this is the right-hand side. And so now we're finished. Now we have definitively proven that the specific solution that we found in orange over on the right, this solution, is in fact the correct solution to this equation, or is in fact a correct solution, we should say. There may be some other solutions which also satisfy this equation, but this is definitely a solution to this equation, and we found this using integrating factors. So this question looks a little bit complicated, especially the check. The check is really messy. It's not very hard as far as a differential equation goes. The working is just messy. You have to be very careful not to lose a sign, gain a sign, lose a term, accidentally mistranscribe a number or something like that. That's a very, very common type of mistake that students have. So this is a sort of first year, second year type of question. It's not a very hard first or second year question, to be completely honest. Maybe for a first year course it's a medium difficulty question, but for a second year course this is a pretty easy question. Maybe week 1 or week 2. And it would be expected that you get these right every time once you're at that level. So checking them is a really good thing to do.